Hey there people, this one here is going to cover magnetic fields and how they're generated using currents through straight cables or current carrying elements in loops in solenoids, and how we can calculate the magnetic field strength due to these currents or conventional currents. So over here we have, to start with, a straight piece of wire. It might be something like this, but obviously a conductor, and we have a flow of positive charge. Remember, positive charges don't flow, it's actually the negative ones. But what we're going to do is consider the direction of conventional current. So the convention is positive to negative, even though we know that's not the case. So what we do is look at the direction of conventional current, and we use the right hand rule. So here it's going to look like that's my left hand, but it's actually my right hand. We put our thumb in the direction of the conventional current, and our fingers would wrap around that current carrying element like this. So on the right hand side we would have a magnetic field going into the board or into the screen, and on the other side it's coming out of the screen. So it's actually kind of continuously looping around like this. Alright, so this will give us the direction that that magnetic field is at any point in 2 or 3D space. If we take this straight conductor here and we bend it into a loop, what we have is something like this. So here we have, it's just a horseshoe shape, doesn't really matter the shape. We have a conventional current flowing around it in this sort of direction, which means that if we take the right hand rule again, at any point here we can have the direction of the current. So if my thumb was pointing upwards at those points, the fingers would wrap inside and come on the outside like this. So that's how we set up that's how we can determine the direction of the magnetic field. If I was to make the current stronger, so if it was twice as positive and twice as negative, all we're going to do is make the field strength twice as much. So we could draw that kind of like this. If we were using a solenoid situation like this, we'd be able to draw twice as many field lines in that space. Alright. The third and final version is this bunch of loops. So it's like this, they're just stacked on top of each other and connected end on end on end. It's called a solenoid. So what we're going to do is look at a spot on here, and because it's 2D drawing rather than 3D, it's really hard to do that in this sort of situation. What I'm going to do is look at a specific point, and I'm going to look at the point just up here. So on this point here, the current is going, so positive to negative, so it's going in this direction, and from where I am, that's going into the board at that point there. So my thumb would be pointing in the direction of the current, and the field would be wrapping, similar to this, on the inside, like that way. So it would be going on the inside and then onto the outside. Inside to outside, inside to outside, inside to outside, kind of like this, all the way through here. Alright? And on the bottom, it's actually going to be going the opposite direction. So it's going to be going like this, because at the bottom the current's actually coming up the other way. So you can hopefully see that when we add all these field lines together, remember magnetic fields are vectors, we draw vectors. If we add all these things together, you can see that on the outside of our solenoid we've generally got field lines in these directions, like this. Should give ourselves more space. And on the inside we've got them going like this, so in this direction, and on the outside we're going back to the other end here. So in this case here, that's how we can develop a nice strong magnetic field. You'll notice that you can draw a bunch of field lines and stuff on the outside here, and you would probably make one a little bit better space than I have. But those field lines all loop back, and through the center we actually have an awful lot of parallel lines, and they're condensed in a really tight space. And when we have this sort of region here, or this sort of region here, we've got lots and lots of field lines per unit area, which means we've got a really big magnetic field strength. So if we ramp up the current, we can actually create a bigger field in that small space. Alright, so now we can look at B being proportional to I, B being proportional to 1 over R. So if we are using a really big current in our straight conductor, our loop or our solenoid, we're going to have a pretty big magnetic field strength. If we are nice and close to our thing, straight conductor loop solenoid. So if we're not far away, so R is small, we're actually going to get a bigger magnetic field strength as well. So if we can do both of those two things, we can have a nice tight spiral here, nice tight solenoid here, and we can have a really big current going through it. We can have a pretty significant magnetic field, big enough that we can lift up car bodies and all that sort of stuff with massive big electromagnets. Alright, so straight cables loop solenoids are the same thing. They're just more complex versions of the other, and instead of being proportional to one on R squared, in this one here the magnetic fields are proportional to 1 over R, and obviously the current. Cheers.